Okay guys, just going to get started here. So this is 4.1 out of our book. For simplicity, I can't get any software that's going to allow me to write on the screen, so all the notes I've pre-hand written, and we're just going to kind of go through each one and we'll talk about each example in question, and then you guys can email me with questions or anything along those lines. So 4.1 starts us out with antiderivatives. So that means we're going to go the other way, right? We spent 2 chapters taking derivatives and finding derivatives of different functions, trig functions, polynomials, and those sort of things. Now we're going to be able to go the other direction. So this kind of stems from when we talked about getting a position graph versus velocity and acceleration. Now I might give you the acceleration, ask you to find the velocity, or I might give you the velocity and ask you to find the position. So we're going to be able to go back and forth both directions here. So kind of scrolling down through the notes here, if we look kind of in the middle of the page, we have f of x equals x cubed. Alright, what we need to know when we separate these out is that a capital X means we're going to be, or a capital F means we're going to be doing the antiderivative, where we have like the lowercase f or the apostrophe, right? That's going to be us doing the normal derivative. So we have to be able to go back and forth. So if we notice f of x equals x cubed, okay, that's the position function, and then to the right of there we have the derivative with respect to x cubed, or derivative with respect to x of x cubed is 3x squared. Notice that we should be able to go back and forth. So on the right hand side we've taken the derivative, and if we take that piece that's on the right hand side, that term, that 3x squared, and we take the antiderivative, we should end back up with x cubed for that. Alright, so in this first section we're going to be referring everything to a lot of the antiderivative. It really just means that we're going the other direction now. Okay, so there's some important factors. When we do an antiderivative, there's generally some sort of constant that we've taken a derivative of that ends up in 0. And until we get initial conditions in a little while, we're always going to have to remember to add the constant c in. So let's talk about our initial example 1 here. It says find the general solution of the differential equation y prime equals 2. So here I've given you the derivative. The derivative is 2. So we need to work backwards and actually find what the equation of that function is. Now if you remember from earlier chapters, when we took the derivative of like a 3x or a 5x or a 10x or a 100x, the derivative of anything with x would just be that constant in front. So when we undo a constant, we're going to put an x next to it. So hence, if we look at the general solution down here, the antiderivative of 2 is 2x plus c. That plus c is there's probably some constant we took a derivative of that got us a 0, so it went away. So that's why we call this the general solution. The general solution will always incorporate a plus c. So from this first example, we should really know that anytime we're taking the antiderivative of a constant, really we just need to put the variable next to it, so in our case x, and then add a plus c to get the general solution. So that's why this is y equals 2x plus c. Alright, let's take a look at the next example here. We want to find the general solution of the differential equation dy dt equals 9t squared. Well, first we got to set it up so it's in a good equation form. So we're going to rewrite it so it's in the form of dy equals 9t squared dt. Now, we have to be able to undo the t squared. We're going to get into how this is. I know I have it a little bit below there, what the power rule is. But when we undo 9t squared, we're actually undoing the exponent rule, which means that we are just going to add 1. Remember when we took the derivative, we subtracted 1, alright, and we brought the exponent down in front and we subtracted 1, and that was the derivative. Well, we have to undo that. So looking at example 2, or if we're working backwards, okay, we're undoing the power rule. So if you notice down at the bottom, I have capital F of x equals x to the n plus 1 over n plus 1 plus c. or if there's a constant in front, I've written it on the right hand side where that k represents a constant, so if it's a 2 or a 3. So to undo the power rule, we not only add 1 to the exponent, we have to do division by whatever that value is so that it works out when we take the derivative. So noting above, alright, we have 9t squared dt, right? So in order to do that, if we apply what's down below, it's more the one on the right hand side that has the kx to the n plus 1 over n plus 1 plus c. N is our starting exponent value in this case. So at the top, if we're still looking at example 2, I have 9t squared. Well, 9 is what our k is, and the 2 is what our n is. So we're going to go 9t to the 2 plus 1, which is 3, so that's why our exponent's 3. And then we have to divide it by n plus 1, which is 2 plus 1, which is 3. But 9 divided by 3 is 3. So that's why we end up with 3t cubed. And then since it's a general solution, we have to put plus c, because if we were to take the derivative of y equals 3t cubed plus some constant, that's what we would get. That constant would fall away when we take the derivative, because remember, the derivative of any constant is 0. That's all I'm going to talk about for this chunk. I'm going to try and break these up into chunks so you don't have to listen to an hour video. So this is 4.1, lecture 1. We'll break it up into multiple lectures.